So now after reviewing average rate of change, which is kind of a pre-calc concept, we're going to talk about instantaneous rate of change. So this fact that we're doing a single instant is what's going to turn this into a calculus concept. So it's a big wall of text. Don't worry about writing all this down. So I'm just kind of explaining what the difference between average rate of change is and instantaneous rate of change. All right, so let's use driving a car as an example. All right, if you leave from your home and you go somewhere else, you're kind of going from point A to point B. And let's say you went 10 miles and it took you half an hour. All right, so 10 miles and half an hour means you're going 20 miles per hour that time. All right, so I can find the average speed you were going. All right, at some points you might have been going 40 on a bigger road. At other points you might be going 10 because you got stuck in traffic or something. But on average, you were driving 20 miles per hour. So this is the thing we did in the last video, all right, the average rate of change. But as you're driving, all right, your speedometer is going to give you some reading that says how fast are you driving right now. Maybe it says 20 sometimes, maybe it says 45 sometimes. All right, but this is the instantaneous speed you're driving right now. How fast are you driving? All right, this is different than average rate of change because average rate of change uses two different points, kind of the starting point and the ending point. Instantaneous speed only uses 1 point. It's just what's happening is at this one moment in time. All right, so our average rate of change formula isn't going to really work anymore because we need two different x values, but we only have one moment. So this is what calculus is going to allow us to do, go from having two different values to just one single value when we're talking about a rate of change. All right, so how are we going to do this? Well, with limits, what did we do when we first did a limit? If we had like limit as x approaches 2 of x squared. All right, how do we do this? Well, we plugged in stuff that's close to it. We did like 1.9, and that goes to something. We did 1.99, 1.999, and we see these were all going to numbers that are about 4. All right, so by getting closer and closer to the x value I care about, that would actually figure out what the limit was. So this is how we started out with doing limits. And we're going to do the same basic idea for instantaneous rate of change. So let's say I wanted to figure out the instantaneous rate of change at 6. All right, well, I can't do that because 6 is just 1 point. I can't use my slope formula. All right, whenever we're talking about change, we're going to have to think about slope. But what I can do is I can pick another point here and figure out the slope between those two lines. All right, so we're going to get this secant line like that. But that's not a very good approximation because 6 and 7 are pretty far apart. So then I can say, well, let's pick a point here. And those values are closer together, so it's going to give me a better approximation for the actual slope that's happening. I can get a point even closer, look at that line that connects those two, and get a point really, really close, and get that line there. All right, so by basically moving the points closer and closer together, we're going to turn our average rate of change into an approximation for the instantaneous rate of change. All right, so this is kind of the calculus idea of things are getting so close together they disappear. When we're doing limits, we weren't exactly at 2, but we get really close to 2. Same thing here, these 2 points, we can't make the exact same, so we get them as close as possible together. All right, so there's 2 different ways you can do this. All right, we're trying to find the instantaneous rate of change at x equals a. All right, well, the first thing, the second formula here is kind of what we were just doing. We take b and a, are 2 different places on our graph, and we just move them closer and closer together. So we want the second value b to just get closer and closer to a. So it's exactly the picture we had in the last slide. But the one that's going to end up being actually more useful for now is this first one. So here we're going to have a, and then h is just going to be some distance away, and this is going to be a plus h. Right, so a plus h is going to start there, and if we shrink h to be 0, this value is going to get closer and closer to a. All right, so we have our kind of starting point a, we have a little bit extra added to a, and if we make that little bit extra go to 0, we're going to get our instantaneous rate of change. All right, so this right now is kind of the formula you want to have memorized or start using when we're doing instantaneous rate of change. So in this example, we're going to find the instantaneous rate of change of our function at x equals 2. We're going to do it in 2 different ways. So we're going to do it the approximating way using the average rate of change, and then we'll do it using this limit definition. So the approximating method, basically we pick 2 different points, but we want those points to get closer and closer to the point that we want. So we can start with like x equals 2 and x equals 3. All right, those aren't very close. They're a whole 1 unit apart from each other. So next we could get them closer together. We could do 2.9 and x equals 3. So those are closer. And just for the video, we'll just do 3 examples and x equals 3. All right, so the x values that we're choosing are getting closer and closer to 3. And then we're going to see what happens to the average rate of change. So the average rate of change, again, is when you plug in the 2 values on the top, and then you take the x values on the bottom. All right, so when we're just looking at the big gap between 2 and 3, the average rate of change between those two x values is 5. All right, I'm not going to fully work out these next ones because the decimals, but if you were to put these in, or you're squaring 2.9 and subtracting it from 9 and everything, you end up getting 5.9. And the same thing here, except for now you're doing with 2.99. And if you put all that in, you end up getting 5.99. So as we kind of go down the page, our x values get closer to 3, right? We stick at 3, and the other one's getting closer to 3, so we're kind of shrinking the gap for our average rate of change. And what's happening to our average rate of change? So as we get our x values closer to 3, our average rate of change looks like it's going to 6, right? 5.99 is really close to 6. So for our instant rate of change here, our guesstimate would be 6. Right? We think that is the instantaneous rate of change at 3. And now we can confirm that using the limit definition. So the limit definition is going to look like this. All right, so we have just a little bit of a distance away from 3 and f of 3. Again, that just means we're going to plug in 3 plus h into x. So we're going to get 3 plus h squared minus 3 squared. And remember that 3 plus h squared is 3 plus h times 3 plus h. So we have to FOIL that out. So when we FOIL that out, we're going to get 9 plus 6h plus h squared minus 3 squared is 9. All right, and one tip to know that you're doing these things correctly when you're doing these limit definitions is everything without an h generally cancels out. And why is that helpful? Well, really from the beginning, we're trying to cancel out this h on the bottom because we want to plug in 0. We can't do it right now because there's an h on the bottom. Right? What we can do now that we got rid of everything that doesn't have an h is we can factor an h out on the top and then cancel that h out. And just like when we were doing limits before, once you cancel out the thing that was giving you trouble, now I just plug in h equals 0 and I just get 6. All right, so that confirms that our guesstimate was right. The average rate of changes are converging to 6, and this limit definition confirms that our instantaneous rate of change at this point should be 6. All right, and then we saw that average rate of change was related to the slope. I actually mentioned this in this video as well, but instantaneous rate of change also ends up being slope. All right, but it ends up being the slope of the tangent line. So in the example we did, we wanted to find the instantaneous rate at 6. Well, the tangent line is going to be the line that kind of just touches your graph in the directions it's going. It's going to look something like this. It just touches that point, right, and keeps going. So the slope of that line would be the instantaneous rate of change at 6. All right, so average rate of change is the slope of a secant line, which would be if you connected 2 different points. All right, that would be a secant line. A tangent line just touches your graph at 1 point. And that gives you instantaneous rate of change. All right, so those are your kind of 2 different changes that we're going to have to deal with. Of course, in the calculus, we care more about the instantaneous rate of change, but average rate of change still is important. It'll still come up sometimes.